Okay, cool. Let's get started. So this week, today we will talk about Fourier series. Basically, it's another way to explain the periodical functions. So we learned in calculus, any function can be expanded using Tanner series. Right? Some coefficients and xn, or if you want to expand, specific point x naught, then something like this. So in this case, you're choosing the basis as 1x squared dot. So if, for example, if your function is a periodical function, meaning that let's here assume the period is 2 pi, then we can expand this function using the basis 1 cosine x, cosine 2x, dot and sine x and sine 2x, something like that. So we write this 1 using a naught over 2. This 2 just for convenience. And the sum over from 1 to infinity, an cosine nx plus n equal to 1 to infinity, bn to sine nx. And an and bn is determined by some integral, which is, I think, pi from minus pi to pi, and fx cosine nx dx, and this one, bn is similar. Basically like this. And yeah, so the reason why we want to expand this kind of function in terms of sine and cosine, one big reason I think is because sine and cosine is quite important in physics. You know that for general system, like assume the potential is like this, and we have a particle or some degrees of freedom. So of course, in equilibrium, it's in the ground state. And if you perturb it slightly, then it will oscillate. And the solution of this motion is usually given by the sine and the cosine, right? This omega is a frequency. The frequency actually corresponding to the curvature of this potential at the equilibrium point. It's very common. Okay, so this is some basics about the Fourier series expansion. And another thing I want to say is the analogy between the this expansion with the vector. So we know that for any vector, assuming this is a vector space, and each element in this space is a vector. For example, this one is vector V. This vector is vector, let's see, vector P. And there's also some vectors which serves as basis vector, E1, E2, and E3, something like this, right? So here we have a similar structure. Actually, it's also a vector space. In this vector space, okay, so there's some function gx, another function fx, and also some constant function 1, and also sine x, cosine x, cosine 2x, sine 2x, stuff like that. The only difference between this vector space with this vector space is that for this cosine sine vector space, the dimension is infinite, right? Because they're infinite number of bases. So 1 cosine x, sine x, cosine 2x, sine 2x, and you can, there's infinite many bases. And similar to what we did in the vector space, we have inner product, right? P dot V dot P, which is written as the sum over all the components, VI and VI PI. Similarly, we can also define an inner product in this vector space. We generally write like this. Assuming all the functions are periodical functions, like the period is 2 pi, then it's minus pi. Okay, so this maybe say it's proportional to this dx. And usually here's a star is a complex conjugate. And of course, if the function is real, it doesn't matter whether there's a complex conjugate or not real. If it's a real function, then the complex conjugate gives itself. Sorry. Another thing is about the basis. We know that we usually choose the orthogonal basis. That means E1 dot E2 is 0, or generally speaking, is I dot EJ is 0 if I not equal to J. So similarly, we have the same thing here. So the dot product between different bases, for example, cosine x and sine 2x, something like that. According to our definition here, you can do the integral. Yeah. So here's cosine x and sine 2x is 0. Or in general, sine nx, cosine nx, mx, or cosine nx and sine mx, stuff like that is 0 if n not equal to m, or sine nx, sine mx, and cosine nx, cosine mx. Basically, all the bases, like by the way, this one can be think of as like it's cosine 0x, right? Cosine 0 is 1. Right? Basically, what I'm saying here is the basis we use to expand the periodic function are also orthogonal to each other, right? And then we know for general vector, we can write this vector in the basis we choose, right? Something like that. So this is just V1 E1 plus V2 E2 plus dot dot. Similarly, any function we can also write as A naught. So there's a basis 1, but for convenience, we scale to 1/2. It doesn't matter. Plus A1 cosine x plus A2 cosine 2x plus dot plus B1 sine x plus B2 sine 2x plus dot. So you can see, so here this is the basis. This is the basis. And this V1, V2 are coefficients, like A0, A1, A2, B1, B2 are coefficients. They're kind of similar. Any questions so far?
So the major difference here is that normally when you're in the vector space, you could have 3 orthogonal unit vectors like E1, E2, E3, and it's like finite. But in
Right.
this, you have an infinite amount of cosines and sines with varying periods.
Exactly. Yeah. Right. You're right. Yeah.
Okay.
Yeah. So basically, what I'm saying here, the structure, the mathematical structure are the same actually, and the only difference for the vectors, for example, we usually say okay, n-dimensional vector thing, the basis, the number of bases is n, right? So for 3-dimensional space, the number of bases is 3. So E1, E2, and E3. But for a function, for periodical function, let's say the period is 2 pi, then there are infinite many bases, like 1 cosine x and sine x. You can write down all the sine and cosine functions. And under this kind of inner product definition, they are also orthogonal to each other. And we, similar to what we did like in the vector space, we can write a vector in terms of this kind of a form. We can also write any periodic function using the basis.
And I had a question.
Sure.
Are we stuck with n being integers here?
Sorry. Which integer?
We're not considering the argument of the trig function to be any real, right?
No.
Right. So n has to be an integer right now.
Right. You mean the you mean here this kind of n?
Yeah, n and m. Yep.
Oh, right. Yeah. Of course. This is because we choose the period to be 2 pi, right? If it's not 2 pi, in general, if it's L, then this kind of basis becomes 1 cosine 2 pi over L on x, and the sine 2 pi over L x, and the cosine 2 pi times 2 L x, and the sine 2 pi. Basically, yeah, you just times n. Something like that.
I'm a little confused about the basis.
Uh-huh.
In the vector space, it's E1, E2, E3. What
Right.
about the vector space on the right?
On the right, the basis is 1 cosine x, sine x, cosine 2x, sine 2x, and in general, it's cosine nx and sine nx.
But we have infinitely many bases on the right, but we have
right. That's the difference, right?
Dimensional bases on the left.
Yeah. Basically, this is an infinite dimensional vector space.
Shouldn't we have the same amount of bases, or
No. They are not the same. They are not the same vector space. For example, if I'm in 2 dimensions, then there are only 2 bases. I'm in 3 dimensions, then it's then there are like 3 bases. Now, if I'm in an infinite dimensional vector space, then there are infinite many bases.
Oh, okay, thank you.
Right. Yeah. The point of what I want to make is they're kind of similar, and you can regard this kind of 1 cosine x and sine x as the basis of this infinite dimensional vector space, and any elements in that vector space is a periodical function, and we can expand that periodical function using this basis. And also we know that in this kind of for the vector, to get a coefficient, we just need to v dot with, for example, if we want to get the v1, then we just need to dot the e1 on both sides. We get e1 times e dot e plus v2 e2 dot e1 because this kind of basis are orthogonal, then all the term goes away. All terms just go away, and only left the first term here, which is v1 e1 dot e1, and v1 therefore is given by v dot e1 and e1 dot e1, right? So similarly, what we have here is quite similar. For example, if we want get the coefficients of A1. A1 is also given by the inner product of this guy. Here is the fx, and also the corresponding basis, which is cosine x, and also the inner product of this kind of basis, which is cosine x. Cosine x. If you write it down, it's given by plus pi and minus pi, and fx cosine x dx, and this is minus pi to pi cosine x squared dx. This is actually what we wrote down before, which is actually the pi. Right. Remember, this is what we wrote down here.
So I just had one more question. So I understand that we're supposed to have, infinitely many sine and cosines because, the basis requires infinite terms.
Right.
Why should n in that case be like the natural numbers, and why is it not like the real numbers? Why are we allowed to have it just be cosine 1, cosine 2, cosine 3 instead of cosine, all the real numbers?
Okay, so that's a very good question. Just because we are talking about periodical function with period 2 pi. So basically, let's say, so if I have a function which is period 2 pi, then if I want to expand this guy in terms of cosine and sine, if this guy, for example, let's cosine nx. Okay, so let's, instead of saying it's any integer number, I say it's any number p and plus bp and sine px. But if you want to impose this constraint, basically x plus 2 pi, which is ap cosine px plus 2 pi plus bp sine px plus 2 pi. This guy equal to gx, right? Gx is this guy plus p sine px. If you want to impose this equation, then you will find that your p must be integer or equal to it's an integer. Otherwise, this guy will not hold. This equation will not hold. This is
I have a question.
So
how do we know the period of by looking at the function, and how does the function change with the period?
Sorry, can you repeat your question?
So how do we know the period by looking at the function itself? And how does the function change with the period?
Okay, I mean, how do we know the period of this function g?
Yes, or any functions.
For any function, I mean, you need to check it, right? For example, of course, for this class, I think if you have a function, it's very straightforward to say whether it's a periodical function or not, right? So for like I don't know, for example, if you have this kind of function, then it's periodical, and in general, you just need to draw the graph. Then if there's some period repeating the itself, then it's period, right? Yeah, I'm not sure what else we can say beyond that.
Because the period is not always 2 pi, right? Of
course not. Yeah, that's what I'm saying here. If it's not 2 pi, if in general, let's say if the period is L, then the basis becomes 1 cosine 2 pi over Lx, and in general is cosine 2 pi Lnx, and sine 2 pi Lx, and sine 2 pi Lnx becomes like this. This is because when you say your period is L, corresponding to fundamental frequency 2 pi over L. So if you denote this guy as the as omega, then basically you're writing as the basis as 1 cosine omega t, cosine 2 omega t, and things like that, and sine omega t, sine 2 omega t. And yeah, if L equal to 2 pi, it's just a special case. L equal to 2 pi, omega becomes 1. So there's no omega, and it becomes cosine t and sine t, and yeah, or x, doesn't matter.
Thank you. I see.
Yeah. Of course, 2 pi is just a special number. Yeah. So what else I want to say? Yeah, so the point I want to make here is the this kind of expansion is similar to what we did in the vector. It's always good to relate what we are learning to something we are familiar with, right? Okay. By the way, there's a very good point. If your function, if your function is not periodical, for example, meaning that your period is infinitesimal small, basically, if your L goes to 0. Then it becomes a Fourier transformation, actually. Yeah, but yeah, we can talk about this next time. Okay, so there's another, of course, you can choose another basis in the vector space. Basically, it's another set of bases that is very useful and common. 1 EINX. Of course, we assume the period is 2 pi. If it's not 2 pi, then you just change this n to 2 pi over L times n. L is a period. So similar to what we did before, you can define this kind of inner product as this. And then you will find that this basis is also orthogonal to each other. So now this complex conjugate is important. It becomes minus INX plus, which is 0 if n not equal to n. And any function any periodic function can be expanded using this basis. And the coefficient can be given by this form, like what we have before, which is 2 pi like this. Yeah. So we mentioned before that the Tyner series actually can be also think in this way, but the difference is for the Tyner series, the basis is 1x squared and in general xn. this basis is not orthogonal. Or of course, it depends on how you define the inner product, but it's generally speaking, it's not orthogonal, and there's no such nice properties for the coefficients. For the coefficient here, just like what we did in the vector decomposition, for this kind of for the component, we can write in this form and calculate the coefficients very easily. Yeah. For the Tanner series, of course, in that case, the coefficient is given by the nth derivative evaluated at some point at x0. But it's quite different from what we have here. This is because for the Tanner series, the basis is not orthogonal to each other.
What's the point of making it putting in the negative? I mean, in the complex thing. What is the physical meaning of doing that?
You mean like this kind of a complex conjugate?
Yes.
Okay, so here basically, I think okay. If you want to ask the physical meaning, I don't think there is a very obvious direct like a very direct physical meaning. The reason why we do it here is you can say here we are defining the inner product, right? Under this definition, this basis exponential INX becomes orthogonal to each other. So there's a minus sign. Then if n not equal to m, is 0. Of course, if you can say, okay, I define another inner product, which is basically like this, without this kind of a complex conjugate, then this guy becomes a plus sign. So this guy is not 0, only when n not equal to minus m. Then it's something that is not that useful for us because we want orthogonal basis. And yeah, basically if you are n equal to m, for example, if your n is 1, m is minus 1, they corresponding to different bases, and we want them to be orthogonal, but under this definition, they are not orthogonal. The result is non-zero. Yeah, this is a good question to ask, but I'm not sure.
Sorry, can you I want to see the picture of the EN INX. Yeah. Thank you. Let me take a picture. I see.
So quick question, G.
Uh-huh.
So N and M represent like the general coefficients to have like in the exponent, and then you're saying that in order for it to be orthogonal, that n must be equal to minus m, or it shouldn't be.
Oh, so here, under this definition, if you define your inner product, this is how we usually define the inner product between two functions within the vector space of a function. So here's a star, and under this definition, this is the result. So this result tells us the basis is a orthogonal basis. So if the different bases, then they're orthogonal to each other. Like similar to the vectors, like E1 and E2, they're orthogonal to each other. So basically, this equation is EI dot EJ is 0 only when I not equal to J. Basically, that equation is the same thing as what we have here. So this is the basis, this is the basis. The inner product of those two is 0 when they are not equal.
But don't we end up having e to the INX and e to the minus INX when we end up writing with the complex coefficients? Like we don't have an I and an M, we just have N, right? When we finally write the Fourier series out completely.
Wait, so
like for the sines and cosines, you don't have like cosine n, sine m. You just have a bunch of n's. So isn't it going to be the same thing for e here? Like, how do you go from n and m and then just to n?
Wait, so okay, so what I'm saying here is the okay, we can expand this function, say an expansion of n x. This is nothing but you can, of course, you can write it in terms of -1 e minus 1 minus x plus e0 plus c1 exponential ix plus e2 exponential 2ix, right? So what I'm saying here is this is the basis, this is the basis, this is the basis. Here's times 1. This 1 is also basis. They are orthogonal to each other, similar to what we have. Like, of course, you can expand it in terms of a naught plus a1 cosine x plus a2 cosine 2x. So this is the basis, and the basis. They are orthogonal to each other.
Okay, yeah, I see. I understand. Thank you.
That's the statement that I want to make. Yeah. Okay. So I hope this helps. This helps you to understand this kind of expansion feather by relating this to this kind of vector space. Okay, so let's do some examples. This is a very simple one. You can take a look at the problem, then we can go through together. Okay, so basically, of course, first you can draw this picture. Sometimes the picture can give you some insights. So from minus pi to 0 is 1. And from 0 to pi is 0. Let's use another comma. Something like this. Of course, you can do it directly. But by drawing this picture, we notice that by shifting this function by one half, so f minus 1/2, we get a odd function, right? Here's 1/2, here's minus 1/2. Something like this. And the reason why we want to do this is because we know that fx, when we do expansion, n cosine nx plus n bn sine nx for fx minus 1/2. This is an odd function, meaning that a naught is 0 and an is 0. Right? So we only need to calculate bn. So basically, the symmetry simplify our life. We only need to calculate this kind of bn. So any question about this part? About this step?
Can you just explain that one more time, please?
Yeah.
Like the even on the odd part.
Yeah, sure. So we know that so any function in general is not even and it's not odd. When we do the expansion, we notice that okay, so let's write a general function as this, and this. So this part is the even part, meaning that if you change your x to minus x, this part will not change the sign. This part is an odd part. If your x becomes your minus x, then the sign change because there's a sign function, right? So now we have by shifting like a minus 1/2, because this original function becomes, this function is a odd function, meaning that the even part is 0 to make this original function a odd function, right? So we must have this form. Oops. Is it clear?
So you look at the graph and then you say it looks like an odd function, and then you go back to the equation, say that part equals to 0 because it's an odd function. Is that right?
Right.
Can we use this technique in the exam?
Of course, yeah. Yeah, you just need to, yeah, this is I mean, whenever you notice that there's some symmetry in your problem, it will always helpful to invoking that. It will always simplify your calculation or not, actually. So so once we have this, we can write down the the formula for the coefficient, which is pi integral from minus pi to pi, and the sine nx f(x minus 1/2 dx). Please stop me if you get confused for some steps. So pi. Okay, so now we need to, because the original function is a piecewise function, so we split into two integral, which one is from minus pi to 0. And another piece is from 0 to pi. So from minus pi to 0, this fx is 1, right? Then it's just 1/2 dx plus pi to 0 sine nx. From 0 to pi, this guy is 0 with minus 1/2 dx. This integral is relatively easy. So it's something like this. Sine nx dx minus 1/2 from 0 to pi sine nx dx, which is, what's this? It's from minus n cosine nx 0. This is minus n cosine nx pi to 0, right? And if you simplify, if you simplify this, you would get pi n on the numerator is this. Yeah. Okay, so now you can plug back. This guy equal to n. The coefficient is this, and the times sine nx. And of course, your fx is given by, you just move this part to the right-hand side. So any question about this problem?
Sorry, how did you get f minus 1/2 in the beginning?
Oh, okay. So this is our original function is like the graph looks like this, right? Is from minus pi to 0 is 1, from 0 to pi is 0. So you just repeat this kind of a function. Then we notice that if we define f minus 1/2, then it becomes 1/2 from minus pi to 0, and minus 1/2 from 0 to pi. If we regard this guy as a new function that's denoted as gx, then the graph for the gx looks like this. And we notice that this is the odd function, meaning that the even part are 0. All the terms in the even part are 0. So we only left with the odd part. So basically, we notice that the gx is the fx minus 1/2. So it's like this. Then we determine this Bn using the usual formula and do the calculation, and then pack back and we get the result. Yeah, is it clear?
Yeah, that makes sense. Thanks.
Sure. Yeah, of course, you can approach this problem like a mindlessly. You just you can write down the fx equal to a naught plus sum a x and x plus sum b sine nx. Then you calculate a naught according to that formula, and an using that formula and bn using that formula. You will find that an is 1/2 when n equal to 0, and is 0 when n is not 0. And the bn is the same thing we did below, right? So it's the -1 and pi, something like that. Yeah. So here,
So for the sine x, we only get negative like 2 over n pi when there's when n is odd, right?
Right. You're right. Of course, yeah. You so here you can simplify it further. When n, meaning that so n equal to 2k plus 1. So it's the k from 0 to infinity minus 2 pi 2 k plus 1. There's 2k plus 1. Yeah, you can simplify your result like this. Is this what you're saying?
Yeah.
Yeah, sure. Yeah, because this is kind of a -1 and -1. So if n is even, then it's 0. And this term is non-zero only when your even is odd. Your n is odd. So here I assume n equal to 2k plus 1, and the k from 0 to infinity. And then so k from 0 to infinity, and I plug this n equal to 2k plus 1, then here becomes 2k plus 1, 2k plus 1, and the minus n becomes 2k plus 1 minus 1. This guy is -1, which is -2. So I replace this guy with -2. Yeah. Okay. That's okay. By the way, you can also check the Dirichlet theorem. We know that you can we know that the expansion should converge to this middle point, which is 1/2 for x equal to 0 or x equal to pi or n pi in general is n pi. Right? So you can say if you plug x equal to n pi into our expansion, you will find the result is indeed is 1/2. Right? Because sine 2k plus 1 n pi is always 0.
Wait, why did you set n equal to 2k plus 1 again?
Oh, it's because if n is okay, so look at this. Let's use another color. Look at this term, especially this numerator. If n is odd, sorry, if n is even, for example, n is 2, then minus 1 to the n power minus 1 is always 0. So only when n is odd, the term is non-zero. So we set this n to this kind of a 2k plus 1.
That makes sense. Thank you.
Yeah, whenever you have this kind of factor in your expression, you can always simplify it further by specify your n is odd or n is even by, yeah. For example, if it's a plus 1, then this term only non-zero. This term is only non-zero when your n is even, right? Yeah, it's kind of. But it's okay if you write your final result in this form. Yeah, it really doesn't matter. So another thing is to expand the same function in terms of this basis. So of course you can do the same calculation. We know fx can be written as cn xn, and n is from minus infinity to plus infinity. Cn is given by, there's one thing I want to say, so let me skip the calculation and write down the result directly, which is the final result is minus in 1 minus n. So this is only true for non-zero n. It seems this formula is quite general, right? This formula is general, but when you do the calculation, for example, if your f is a constant, then it becomes like this. Then you always need to do something like this, like the standard stuff from some value A to some value B. In this case, when you do this step, you have assumed your n is non-zero. So the final result is only reliable when your n is non-zero. So this is what was tricky and easy to forget, like when you doing some problems. So in this case, you need to do C0, like separately, which is from minus pi to pi, and fx. Of course, n equal to 0, this guy becomes 1. So it's quite easy. It becomes like this. And for our case, it's pi, which is 1/2. Yeah. Is it clear what I'm saying here? Okay, so yeah, so then you can write your fx in terms of this kind of n not equal to 0. Ix. And you can prove by writing this guy using the the 2i experiment with by writing this guy using like cosine to nx plus I sine nx. You can prove this expansion is equivalent to the expansion we have before. This one. Yeah, another thing I want to say is there are some problems ask you to prove this kind of series equal to a number. In this case, we usually just set this x to some specific numbers and then it becomes the result. In this case, I think you just need to set your x to pi over, pi divided by 2. And then this expansion becomes this. And if you simplify this result, this equation, you will get this equation, this equality you need to prove. And yeah, that's it.
Yeah. So how do you know what value you should set the x to for exercise 3?
Yeah, that's a very that's a good question, and usually it's some special values. You know, it's some like a 0, pi over 2, and pi over 3, something like that. Yeah, you just need to try. Also, there's sometimes you need to set your value to this kind of a jump point, and then you get your series converge to the middle point, and this is also one thing you need to remember. Of course, yeah, you can say if okay, it's kind of messy, but you can say if for this kind of sine 2k plus 1 times x, if you set your x to some weird number, then you won't get a nice equation like this. You need to set some like special numbers to make it look nicer. For example, like this or pi. But if you set it to pi, then it becomes 0. 0, then 0 equal to 0 you will get. And then that's not what we want. So you try this. You will find this guy becomes minus n, minus 1 to k's power. This corresponding to this guy here. And yeah, there's no general, strategy to figure out which x you need to set. You need to observe it, and yeah, try it. Of course, you can also try some other values, but usually it's some special case, It's easy to write down. Yeah, something like that. Yeah, that's it. Any other question? By the way, I will post the solution on the CCLE later. Yeah, so you can take a note. If you have no question, you're free to go. And if you have question, you can stay here. We can discuss.